Improving the accuracy of temperature forecasting in Mumbai, Colaba. Abstract. Background: temperature predictions are of great importance due to their implications for human activities. Extreme heat can lead to dangerous, even deadly, health consequences, including heat stress and heat stroke. Thus, there is a need to predict temperature accurately so that people can be warned about such conditions so that they take the appropriate precautions. Methodology: in this paper, we look at temperature data in Mumbai, Colaba, from 2008 to 2020 and attempt to come up with predictive models for the maximum temperature. We carry out feature selection through filter methods first in order to efficiently use a variety of algorithms to develop predictive models. We use various mathematical techniques such as multiple linear regression, MLR, simple exponential smoothing, SES, artificial neural networks, and an autoregressive integrated moving average, ARIMA, models to predict the temperature. The experimental results are evaluated and compared using the root mean square error, RMSE. Results: on experimenting with all four models, it was discovered that the ARIMA model yields the best predictive model, having a RMSE of 0.25877777 on testing data by removing some noise and an RMSE of 0.8213 with white noise. This model is also optimal as the residuals of this model are a Gaussian white noise, which cannot be predicted. Furthermore, the poor performance of MLR indicates that temperature cannot be accurately modeled through a linear function of the variables considered. Background: this paper attempts to come up with a reliable predictive model for the maximum temperature in Mumbai. Although there are several research papers based on temperature predictive models in general, there were very few papers that aimed to predict temperatures in Mumbai specifically. The models cited in several research papers, for temperature prediction in areas all around the world, were not able to improve on an RMS error of approximately 1 in most cases. Thus, this paper aims to improve the RMS error of these previous models for the dataset of Mumbai, Colaba. In many papers, multiple linear regression and neural networks have been commonly used for temperature predictions, with artificial neural networks being the most common. This paper also explores a variety of time series analysis techniques such as exponential smoothing and autoregressive integrated moving average models. Often temperatures in Mumbai are underestimated and necessary precautions are not taken while exiting one's house. Due to the adverse effects that this heat can have on the health of individuals, it is necessary that steps be taken at an organizational level to issue warnings to citizens so that they can take the necessary precautions and steps before leaving their house. This idea was inspired by the IMD's Heat Action Plan, which has been implemented in Ahmedabad. While the temperatures in Mumbai may not be as severe, precautions are necessary in order to protect and inform individuals about the adverse effects of heat. Explanation of code. We first import the comma split values containing the raw data for our analysis. We then keep only the columns that were deemed statistically significant by the Pearson correlation test. We then carry out the max-min normalization of the data as specified above. We then partition 70% of the data for training our regression model and 30% of the data to test the regression model. We create the multivariate ordinary least squares linear regression model using gradient descent as outlined above. We then calculate the sum of squared error for both the training and the testing data using the regression model found. Since the behavior of our model is similar for the training and testing data, we can conclude that our model is not over or underfitting the dataset. Overall, we can conclude that our data with lag 1 through a linear relationship does not yield ideal results. This multiple linear regression was also autoregressive in nature but did not give us the desired RMS error. Simple exponential smoothing. We will also attempt to forecast temperature using time series analysis techniques. We will begin with simple exponential smoothing as a technique because there is no clear trend or seasonality in the data when the time series is plotted. We don't use Holt's exponential smoothing or Holt-Winter exponential smoothing as our data does not have clear increasing/decreasing trends or any visible seasonality based on the plot. In simple exponential smoothing, we say the predicted observation is a weighted average of previous observations. While calculating the weighted averages, the weights decrease exponentially as lag increases, that is, the smallest weights are associated with the oldest observations. Explanation of code. We first import the comma-split values containing the raw data for our analysis. We then remove all columns except the maxtemp for our time series. We partition our dataset into training data and testing data. We train our simple exponential smoothing model on the first 70% of our data. We test this model using the remaining 30% of the data. We then convert the vector into a time series. We then plot the time series and run simple exponential smoothing on our time series. This gives us the minimum value of. We also find the RMS error of our model on the training data. We then use the same value of. To run our simple exponential smoothing model on the testing data and calculate the RMS error for the same. Metric of analysis for results. We will now be analyzing the results produced by the simple exponential smoothing model. One of the main issues that arises in the use of this model is that it does not perform well on sudden fluctuations in the data, whereas it performs very well for gradual increases or decreases in our data. The high alpha value indicates high dependence on previous day values of the max temperature. The high alpha also indicates that as lag increases, data beyond lag equals 3, 0.8400815, 0.1599185, 3 equals 0.00343571 becomes too small to have relevance to our forecasted value. To determine how well our model fits the data, we calculate the RMSE for the testing data and the training data. We define our prediction model function for simple exponential smoothing to be. The temperature on the TTH day is defined as. The model gives very similar values for the RMS training and testing data, thus overfitting of data is not an issue for our model. Since simple exponential smoothing doesn't help and the data cannot be expressed as a linear relationship, we look at artificial neural networks to explore nonlinear hypotheses functions for the data. Explanation of code. We first import the CSV file containing the raw data for our analysis. We then retain all the feature columns from our feature selection and remove all NA values. We first carry out feature scaling of our data through min-max normalization. We then partition our dataset into training data, 70%, and testing data, 30%. We train an artificial neural network with 2 neurons to fit our training data. We find the RMS error of our model on the training data. We then run our model on the testing data and calculate the RMS error. Results. The neural network plot has been included below with the weights on each wire connecting our input to the neurons and our neurons to the output layer. The value of the bias operator for the hidden layer is 2.44763 and the bias for the output layer is 12.68663. Neural network plot. Metric of analysis for results. We will now analyze the results of the neural network model. The use of neural networks allows us to predict the data using a nonlinear hypothesis function. The high weights on the Winchell C, maxlag1, and avglag1 indicate that these are the dominant features in our learning. A variety of number of neurons were tried out. 2 neurons were chosen as larger number of neurons seemed to overfit our data and would have an overly complicated hypothesis function. To determine how well our model fits the data, we calculate the RMSE for the testing data and the training data. We define our prediction model function for our neural network to be. The actual temperature is represented by. Since the RMS error for the training and testing data using our model is similar, we can conclude that our model does not overfit our data. It also performs better than the exponential smoothing model as well as multivariate regression, but only marginally. Since expressing the forecast value as a linear/nonlinear hypothesis of explanatory variables does not give us the desired results, we try to use time series analysis using ARIMA. Autoregressive Integrated Moving Average, ARIMA. In order to apply the ARIMA technique, we require our time series data to be stationary. This means that our data has a constant mean, constant variance, deviation from the mean, and no seasonality. It is necessary to confirm whether our time series is stationary using the Augmented Dickey-Fuller test, ADF test, and the Kwiatkowski-Phillips-Schmidt-Shin, Kpss test. The ADF test is a unit root test. The mathematics and proofs related to the ADF test will not be described in this paper but can be found in one. For our purposes we only need to know the null and alternative hypothesis as defined by the test. 0. Null hypothesis: the given data is non-stationary. 1. Alternative hypothesis: the given data is stationary. On running the ADF test on our time series we get a p-value equals 0.01. Since the p-value is less than the significance level of 0.05, we can safely reject the null hypothesis and conclude that our data is stationary. However, for large datasets the ADF test can be erroneous, rejecting the null hypothesis a vast majority of the times. Hence, we use the Kpss test to confirm that our data is stationary. We use the Kpss test for level stationarity. For the Kpss test the hypotheses are as follows. 0. Null hypothesis: the data is level stationary. 1. Alternative hypothesis: the given data is level non-stationary. On running the Kpss test we get the p-value equals 0.1. Since the p-value is greater than the significance level of 0.05 we cannot reject the null hypothesis, which supports our previous conclusion that our data is stationary. Since our data is stationary we can proceed by using autoregressive integrated moving average processes on our data to come up with an accurate forecasting model for the data. Since our data is stationary we do not require an ARIMA model and we can directly use an ARMA model, autoregressive moving average. Before we can define an ARMA model we will define white noise. Definition 4.1, white noise: it is an identically and independently distributed stochastic process. Z with mean 0 such that there is no serial correlation between values of stochastic process in the present and past. A Gaussian white noise is when our stochastic process is 0-2. White noise time series cannot be predicted as they are a sequence of random numbers. If the series of forecast errors are white noise it suggests that our model cannot be improved. Figure, plotting the residuals of our ARIMA 2,0,2 model. We used the ARIMA model on our time series and the residuals of our model were a Gaussian white noise with mean 0 and variance 1. However, we want to improve our model despite this white noise. To do this we will attempt to smooth our time series in order to reduce the white noise in our time series. We can ignore some random fluctuations in our data and thus it is justified to take the moving average of our data. We will use a triangular moving average smoothing technique in order to minimize the error caused by this white noise. For this we will define our new smooth time series to be and our original time series to be y. Mathematically our smoothed time series of order 2 will be defined as equals plus 12. To get the triangular moving average, to smooth our time series we apply the moving average of order 2 again. Equals plus 12. Blue, modified time series with triangular moving average. Green, original time series. Explanation of code. We first import the comma-split values and filter only the relevant maxtemp data from the dataset. We then create multiple time series, one containing the entire dataset, one containing the training data, and one containing the testing data. We then use triangular moving averages to smooth these time series. We also run the ADF test and Kpss test on the data to test for stationarity. We then fit the ARMA 2,2 model to our data and calculate the RMS error on the training and testing data. We plot our residuals to observe whether it is a white noise time series to ensure optimality of our time series. Results. According to the ADF and Kpss test we get that our time series is stationary. We get that an ARMA 2,2 model that best fits our data. Coefficients of ARMA model. Metric of analysis for results. We will now analyze the results of the ARMA 2,2 model. To determine how well our model fits the data we calculate the RMS error for the testing data and the training data. We define our prediction model function for our ARMA model to be The actual temperature is represented by equals V, dash 2, equals 1. The plot of our residuals is also a white noise time series. Thus, we can conclude that our ARMA model is optimal as white noise cannot be predicted. Since the RMS error for the training and testing data using our model is similar, we can conclude that our model does not overfit our data and is a reliable predictor even on unseen testing data. It also performs significantly better than the exponential smoothing model, multivariate regression model as well as the neural network model. Figure, plot of residuals of the ARMA, 2,2, model. Results. The results of the research are that the ARMA, 2,2, model works best for prediction of data in Mumbai, Colaba. After the removal of noise, this model gives an RMS error of 0.25877777, which is much lower than the previous values. To outline the reliability of the model, the actual temperature recorded in model predictions were compared for both maximum and minimum temperature in Colaba. To test the model, the predictions for 15 days were carried out every day.